Howdy folks, I'd like to share with you the next subject, and that is I wrote about a year ago, I wrote a science article about the conservation of space-time, energy and mass. And in that I showed that when you speed up an object, whether that's a rocket, whether that's a bullet, whether that's an electron, or a proton, or a neutron, or a muon, for that same token, then some things are happening. In the first place, the mass of that particle is increasing. You put more energy in it, and energy represents some mass. So the mass of the particle or the object is increasing. Next to that, the length in the direction of the path that the object is going, the length is shrinking. That's called Lorentz contraction. And next to that, the time is also slowing down from a still standing observer. And we saw that, for example, with the decay of the muons. That's why I mentioned the muons also, because the muons have a decay time, a half-life of about 2.2 microseconds, something. I'm doing it at the top of my head, but something like that. But if it's speeded up to close to the speed of light, then the decay time, the half-life of the muons is elongated, so that they even reach they are in cosmic rays, so that they even come to sea level where we can detect them. That would not be possible if the time of the survival is not elongated. So time dilatation is also a very known and very realistic phenomenon. But it shows, due to these phenomena, we know that space, time, energy, and mass are thus conserved in some way. And I wrote in that paper that the gamma factor is the key role in it. The same goes also for gravitation. Also gravitation, because the amount of mass which is present in some area, the time slows down and the space is bent. So we see that the same properties also with the gamma factor. But the gamma factor also consists of unit-wise, we see the same pattern with speeding up objects or gravitational effects. We see exactly the same things. So that called in that paper I mentioned that it cries out for a conservation law of some kind. And I've tried to formulate that in a mathematical form. But the thing is, if space and time is conserved with energy and mass, that means that space and time itself contains energy and mass. Now, everybody's looking for the dark energy and dark mass, but with this in mind, what I just told, then I would not be surprised that dark energy and dark matter is actually represented in space-time. That space-time itself is the dark energy, is the dark mass. And now, an obvious reasoning is that for dark energy is that if you look at what space is doing, space is vibrating. Now, if you have a compressed spring, which is also vibrating, that a compressed spring will try to expand. And that's also what you see with the universe. The universe is expanding as if it was a very large compressed spring, and it's vibrating, of course. But from my point of view, the entire universe is like a compressed spring, which represents the expanding energy, the dark energy, which makes the universe expand. And time is also representing some mass, which is called the dark mass. At least it could be a possible candidate of the dark mass. So from my point of view, with this in mind, and also with the whole point of view of the conservation of space-time, energy, and mass in the backs of our minds, space and and time, or space-time, the space-time continuum, are, from my point of view, good candidates for dark energy and dark mass. Well, this is the statement I want to make. Maybe I'm going to write a science paper about it, but then at least I made this statement already on, in this case, YouTube. Okay, this is what I wanted to share with you, and thanks for watching, and see you next time. Hasta la vista. Bye-bye.